No slides?
Well, I'm going to use slides, but I don't know if you're going to see them.
Oh. Sorry about that.
Slide somewhere.
Oh, really? Gonna go away on its own? No. There you go. Want to test the clicker one more time, just back up. Yeah, okay. Okay. Sorry, it's spoilers. Doing the intro? I will.
All right, so we continue our conference. So it's an immense pleasure to introduce Nikita Nekrasov from the group, who is going to tell us about geometric relativistic hydrodynamics and quantizations in chaotic letters.
So it's likewise, it's an immense pleasure for me to speak at this conference. I know for a fact that today is not Maxim's birthday, but it just happens to be my father's birthday, so he's the birthday talk. And but it's mostly dedicated to Maxim, not to my father. So I'm going to report on the work which we have recently undertaken with Pavel Wiegmann from Chicago. And so the starting premise is that many interesting differential equations and ordinary differential equations and partial differential equations actually can be recast in the form of a problem with intersection theory. For example, the silliest example is Hamilton equations in classical mechanics. So these are just ordinary differential equations if we define a number of dimensions. But now I'll present these equations as solving some intersection problem, which is actually not an entirely stupid problem. So first, let's review that. Of course, we will know that these equations can be viewed as the relational equations for a functional, the action functional defined in the space of paths. But not worry about the boundary conditions for the moment. And so this is the functional. It's not always single valued. If the symplectic form is not exact, the functional itself is multivalued, but its derivative is a well-defined one form in the space of paths. So the Hamilton equations are simply the zeros of the differential of this functional. But now let me recast this statement in a more geometric way. So I will introduce now an infinite dimensional symplectic manifold, which is which I will take to be a cotangent bundle to the space of paths. And so the points of the space are pairs, a path, so a parameterized path in the original symplectic manifold, and one form on the path valued in the pullback of the cotangent bundle to the symplectic manifold. So, well, it's a cotangent bundle, so it has a canonical durable form, symplectic form. And so the vanishing of the differential of the action is, in fact, it's a locus where two interesting Lagrangians are manifolds in this dimensional symplectic manifold of the set. One Lagrangian is determined entirely by the symplectic form. It knows nothing about the Hamiltonian, and it's just the set of pairs with path and row. Rows was one form. When this one form is essentially obtained by taking the tangent vector to the path, substitute it into the symplectic form. That way you get the one form, and then you pull it back from the path. That gives you one form on the path. And the second Lagrangian is determined by both. Yeah, sorry. The first Lagrangian as I said, only knows about the symplectic form. It is actually invariant under the reprioritization of the trajectory. So it's almost topological. It only knows about the basic structure, symplectic structure of the original manifold. The second Lagrangian knows about two things. It knows about the parameterization and about the choice of the Hamiltonian. So it's more kind of engineered Lagrangian manifold. And so that just, so this is the formula for its parts. If you can write trivially the generated functions for these Lagrangians in the polarization where everything is represented as functions on the original, on the paths of the original manifold. And so the first, and I'm trying to avoid using the pointer, yeah, because that's what we don't see. So the first Lagrangian, the generated function of the first Lagrangian is the integral of PTQ, and the generated function of the second Lagrangian is the integral of HDT. So I'm just equating the differentials is equal to the technique of setting the whole differential to zero. It's a trivial fact, but it's a kind of beginning of a beautiful friendship. Another example was recently supplied to me by Maxim Zabzin. He observed a similar structure, sorry for my Spanish, a similar structure. So he observed similar structure in the context of sigma models. So if you study harmonic maps of a two-dimensional Riemann surface into some Riemannian manifold X, so the surface is Riemann, meaning it only has complex structure, and target space is Riemannian, meaning it has a metric. And so we solved the Euler-Lagrange equations for the Dirichlet functional, which give us harmonic maps. And the observation of Zabzin is that now we can recast this as the intersection of two Lagrangians in the cotangent bundle to the space of one Jeffs of maps of the Riemann surface to X. So this is a slightly more intricate manifold. It has this flavor of those AKS that manifolds, except that everything is bosonic here. No changes in parity. And so again, so now these two Lagrangians, one of them is purely topological. It only knows about smooth structures of sigma and X. And so this is here I wrote the generated function. It's an integral of sigma of P d gamma. So gamma is a map. P is a one form on sigma valued in the bootleg of the cotangent bundle. And so this guy only knows about the smooth structure. And the second Lagrangian submanifold has a generated function which depends on the metric, the target space, and the conformal structure.
Graph of differential at zero, yeah.
Yes, but so of course, but here the point is that instead of taking zero, but rather splitting the Euler-Lagrange equations in two parts, I separate the structures. So one guy knows about the smooth structure, another guy knows about additional structure, and so I think it's a more fruitful point of view. So it's a separation of, so that's the common theme of these examples. So we separate structures. So one is, for example, one Lagrangian carries smooth or symplectic structures, the basic thing of the ambient manifold, and another is more artificial. So it depends on the Riemann structure or the formal. Charge and state is not just a joke, because a similar story happens in a modern approach to quantization. So the old-fashioned paradigm of quantization, like in geometric quantization, you start with a symplectic manifold together with the algebra functions in this manifold, then you quantize it if you can, and you produce a cubic space or a space together with the representation of some algebra. But in modern view, we should separate this space of states, and the charge, the symmetry structure, the algebra which acts there, because an algebra will have many representations. And so, and that separation between the algebra, the non-conclusive algebra, and its representation is achieved by similar construction, where you have the two types of branes. So in the simplest case, those will be two Lagrangian submanifolds into some ambient space. And so one Lagrangian will represent the non-conclusive algebra, another Lagrangian will represent the choice of representation itself. And so since you can vary the ingredients in this construction, that tells you that one algebra can have many representations, or one space can be acted upon by different algebra. Yes, okay. Yes, sometimes it complicated. So what Maxim is asking, he's asking to translate Russian saying that flies are separate from couplets, from meat. But of course, they're different ends, but sometimes they come together. So this is the point. So here are some other more sophisticated examples, which are well known. The example which I like is Liouville theory. So Liouville theory in 2 dimensions, classical Liouville theory concerns the study of constant negative curvature metrics. Usually the problem is that you're given some metric on the surface, so not just on the remaining surface, and then you try to find the conformal factor. So you want to find the different representative of that conformal class, in which the curvature of the metric will be constant. And so that problem, thanks to Poincaré, actually can be cast in the form of the study of intersection of two Lagrangians in the modular space of flat SL2C connections on the surface, in which we're studying the problem of Liouville theory. So one Lagrangian is the so-called variety of opers. Even though I said it's due to Poincaré, but the opers were introduced maybe 90 years later by Felix von Drizzt. And now we lost the picture. No, I'm sorry. Okay. No. So something. I'm about to say something. Okay, good. So roughly speaking, opers are globally defined second-order differential operators. So the holonomy of solutions of those equations belongs to SL2C, and so you can view them as particular SL2C flat connections. Roughly half of SL2C flat connections can be realized as opers, given a complex structure on the surface. If you change complex structure, the type of holonomies which the opers will produce will change. And so you can locally even fiber the SL2C flat connections by varieties of opers. And now the opers which you get from solving the Liouville equation, roughly by taking the Poincaré's tensor d phi squared plus d2 phi, they will have an additional feature that the holonomy will actually be real. And so solving the Liouville equation implies, in particular, that you're finding opers with real holonomy. So you have intersection, you see an intersection of two transverse submanifolds. They are Lagrangian with respect to the imaginary part of the so-called J-type symplectic homomorphic form. The oper is actually Lagrangian with respect to the full homomorphic form, but let's do this problem. Now, on the same module space of flat connections, SL2C, or maybe even more generally, you can. Oh, sorry, I forgot. This problem of intersecting the opers and real connections was kind of discovered recently by Franklin and Carter, who were studying what's now known as analytic Langlands problem. And we'll call it program. We'll call it problem.
No, in fact, this can be discovered 10 years before that, and I use the intersection of real opers the time of
Of course, I can say the same thing. So I also discovered it, and I also told them very many times, and of course they forgot. But in my case, The excuse is that they don't understand physics and physicists, but I don't know what the excuse in your case. Also, they only study the simplest case, so maybe they already discovered it once again when they allow for non-trivial functions or good instructions. Anyway, but this is a nice. Yes.
Design for SLQC or
there is a similar story for the so-called Toda equations. So they describe some kind of special embeddings of the Riemann surface into the projected spaces of high dimension. So those will be so there will be there is a similar story with some similarity for SLM symplectic connections. And so there is a variety of operas. In fact, for any simple Lie group, there is a variety of operas, and you could also study its intersections with real, with connections whose homology belongs to some real form of your conference Lie group. I don't know the geometric interpretation of those for the general case. For the A type, this is related to this Toda equations. Toda equations phi belongs to the Cartan subalgebra of the Lie group.
it's the same.
It is.
It's the same for both symbols.
Yeah, but what's the geometric interpretation? For the A type, I know that it is some minimal embedding into CPN -1. I don't know whether it's for this is the story. So A type has its minimal orbit, CPN -1, which is DE and that's not have, so it's not clear.
What equation guarantees that these are transverse? The two Lagrangian.
What equation guarantees?
Yeah, why
Generic.
are the
I don't know. I mean, it's fact of life. I don't know what the
why is it that
maybe because one is actually holomorphic in the in some complex structure. So this space of Lie connections has a has actually family of complex structures, and so we could carry it. You could form this complex structure. I'm not sure. It sounds obvious to me, but let's not get carried. So another type of intersection theory, which happens in the same ambient space, but describes a slightly different problem, is the large class of beta ansatz problems, where you study quantum electrical systems, typically some spin chains, the Venn model, or some generalizations of those. And so the equations which describe the structure of these systems, I'm condensing 50 years of work of many people, including Colin, who is here, into just one slide. But this condensation gives you the interpretation of this work as studying the intersection of the same variety of operas, but now a different type of Lagrangian submanifold in the space of flat connections. This time, this Lagrangian is also Lagrangian with respect to the full holomorphic form omega J, and that's defined by some topological conditions, like saying that your sigma surface sigma is a boundary of some free manifold that gives you a Lagrangian in the space of flat connections. So choice of free manifold is a kind of topology which doesn't require choice of complex structure. So what's interesting is that the Pavel equations, and to the less extent, but well, Pavel equations somehow are the result of a marriage between two different structures: a complex structure on the surface and some topological data, which defines the type of quantization you want to choose for your to the space of the connection. Now, the fact that we're doing intersections of Lagrangians in complex manifold, which is classical mechanics, in some sense, of they complexify classical mechanics, and as I claimed, it has to do with quantum, with solving quantum systems as part of some kind of duality between classical and quantum problems. And so the generation function. So here, in these two examples, the common denominator was this variety of operas. And if you have your favorite system of Darboux coordinates on the modular space of connections, you could describe this variety of operas using the generation function. And it turns out that the generation function for operas has some kind of microscopic description. It is actually, so it's a complicated object, but it arises as a limit of something much simpler, in fact, combinatorial, something combinatorial. So one way to look at it is through the theory of classical conformal blocks of Liouville theory, which was put forward by Sasha Samolojik a long time ago. So in Liouville theory, there's this parameter B, which measures the degree in which the quantumness of this theory. And so if you take something which is, I will not introduce, we'll not describe the conformal blocks of quantum Liouville theory, and take its limit when this parameter B goes to 0. So take quasi-classical limit when the central charge goes to infinity. Then the certain asymptotics of the Virasoro conformal block will give you the generated function of this variety of operas. And more recently, actual conformal blocks, well, these are some objects of representation theory of Virasoro, but it's hard to see any structure there. So you just have to work hard and learn some matrices and get it. But it was maybe not so recently now, but so let's say Samolojik introduced classical conformal blocks at the end of 80s, and this goes back to the early 2000s. So these blocks, blocks, and therefore the asymptotics can be recovered from a much more geometrical problem. In fact, here's an intersection theory problem right now on the modular spaces of instantons or sheaves. So here one does equivariant integrations of the modular spaces of instantons, let's say for the group SU2 or the products of SU2 on R4, and you do this count equivariantly with respect to rotations of R4, and then this limit, which gives you classical conformal blocks, is limit when one of the equivariant parameters goes to 0. Other one stays fine. So it's some kind of enumeration of Young diagrams. That's the picture. So today, this was just an introduction to motivation. So my plan is to review for you something from much earlier times. Modular equation describing the fluid dynamics in several contexts. I want to point out some similarities with to much more recent discussions of special harmonic manifolds, and then finally the proposal for interpreting the equations of relativistic hydrodynamics that Pavel Wiegmann and I came with by thinking about again the hard work of many people from much more recent compared to Euler, but much more respectful compared to what I described before. And we'll talk about that. So so that was I don't know, 70 years ago. It was the 250th anniversary of Euler's birthday. So he wrote many years ago. He wrote all kinds of equations, and the simplest equation describes the motion of an incompressible fluid in 3 dimensions. So this is essentially, it's a beautiful set of equations. These are equations on the vector field, and the way he wrote it, actually I don't know how he wrote it, but the way textbooks write them is very much not coherent. It uses the Euclidean structure in R3, and so there is something called the hydrodynamic derivative. So you So there is a time evolution. You measure the vector field at the point in space at the moment of time, and it changes for two reasons. First of all, it just changes, and then this point is being transported to another place. So when you try to measure the velocity at the next moment of time, you actually measure the velocity of a different particle of fluid. So there's the second term of this equation, which is nonlinear, and this is the start of. These are very simple equations, but they study it very hard. And then there is this pressure term, the gradient of pressure, which whose sole purpose in this case is to ensure that the condition that the vector field is divergence free. So P can be computed from V at any moment of time. Why? It's a non-local function of V. So the equation is actually non-local. That's why it's kind of hard to analyze that. Now, they have been recast in the geometrical form, and where you can start separating structures. What's actually used in these equations? So the first point is to give yourself a three manifold with a void form, so-called mu, and the equation deals with vector fields to preserve this void form, and so there is an algebra, there is a real algebra which I call G sub mu. So these are divergence free vector fields. These are vector fields so the real derivative of mu with respect to those vector fields is equal to 0. And inside, so the commutante of this real algebra is a smaller real algebra which consists of exact divergence free vector fields. Those are such that the contraction of vector field in the free form is exact free form. And now it's important to deal with the dual space in the real algebra. And so if you look at the condition that the original vector fields were such that the contraction of the vector field with the void form was closed, then the dual space will consist of one forms modular exact one forms. So I call them P. And so Arnold famously interpreted Euler's equations as a spinning top. So it's a flow on the conjugate orbit of this group of the void preserving metamorphisms, which is determined by some Hamiltonian function. So the conjugate orbit is a infinite dimensional symplectic manifold. It is not so easy to pin down this conjugate orbit. So what's going on here? So you see, if you look at this one form P, which describes a point in a dual space, its derivative, vorticity omega, is it's just some closed effect. It's an exact two form on three manifold, and the Euler equations, when phrased geometrically, imply that the time evolution of this two form proceeds by diffeomorphisms. Diffeomorphisms with respect to the vector field, which we're actually trying to find. But so it means that the whatever motion does to this vorticity two form, it preserves, it moves it along the orbit of the group of void preserving diffeomorphisms. And so that orbit is the conjugate orbit in question. And so by Kirillov constant, of course, it's kind of infinite dimensional extension of Kirillov constant, it is a symplectic manifold. So the Euler equations, even though they are non-local and hard to analyze, they are Hamiltonian equations. The question is, what orbit do we want to do we have? So given initial conditions, they will determine in which orbit we will find ourselves. So there are some orbits which are kind of easier to understand. For example, if I take the kind of extreme case when my vorticity two form is a delta form, like from Carré to a one-dimensional curve, this curve has to be closed for the formula to be closed. So then any knot or any link gives you an example of such conjugate orbit. And so the invariance of the orbit and the analogs of the eigenvalues of the matrix for the conjugate orbits of the group of unitary matrices, those are the invariants of knots in this case, and for the general two forms, we don't have good name for what of those invariants. So, so those words can be maybe. I mean, I like symplectic language and I like Newtonian formulation because then I can use the first slide of my talk that by almost trivially this whole thing would be the intersection of the Lagrangian somewhere, but it is very hard to write the Euler equations in the Hamiltonian form because of these issues with the selection, with orbit selection. It is easier to describe them in the Poisson language. So the dual space to the algebra is canonically a Poisson manifold with linear Poisson structure. And so then it is enough to have Poisson structure to tell you how the evolution takes place, because you just need to compute. If you want to know how any observable evolves with time, you just compute the Poisson bracket of that observable with the Hamiltonian. And so the Hamiltonian for Euler equation is essentially the L2 norm of the momentum, except that remember this momentum P was a one form defined up to exact, adding it to an exact form. So it is not L2 norm is not gauge invariant. So what you do, you take a minimum, so you take an extremal, you find the extremal representative for the momentum, and that's the Hamiltonian as a function of momentum. And so it depends on both the metric and the volume form in this form. This is kind of a sophisticated way of saying that the Euler equations are driven by the energy function, which is just kinetic energy, rho v squared over 2, but cast in a symmetric form. Okay, so this fact that to write Hamiltonian, I have to write something simple, but then find extremum in maybe in the orbit of the actual some differential is reminiscent of a much more modern structure, which I want to make a few remarks about the relation between the hydrodynamics and the Calabi-Yau structures. So recall that this algebra of exact divergence-free vector fields has an invariant killing form. It is invariant, but it is indefinite. So that's why this algebra is very different from the familiar simple algebras. So for each vector field V, you have an associated one form psi, and if you compute the norm of vector field will be just given by the Chern-Simons function of this psi. If I shift psi by something exact, if I work on the closed manifold, the value of the integral definition. So now, if I take another three manifold, not necessarily the original manifold I start with, and I use this algebra of divergence-free vector fields, exact divergence-free vector fields on manifold M as the gauge algebra, I can write the Chern-Simons field theory on M tilde and produce some kind of a hybrid semi-topological field theory, which will be topological on M tilde and will depend on the volume form of M. But nothing else, it doesn't depend, there is no metric involved. So we could call it hydro-Chern-Simons, and it is, so if you do something like a weak rotation, where you treat M and M tilde as sort of holomorphic and anti-holomorphic parts of a complex three manifold, then you get the celebrated Kodaira-Spencer theory of Beshatsky, Chakotay, Gurevaffa, which describes the B variations of Calabi-Yau three structures. So you see, the manifold M had a volume form. So if you now state this in the language of complex geometry, if M is a holomorphic part of a complex three manifold, and the volume form now is a holomorphic volume form, let's give you a Calabi-Yau structure. So Calabi-Yau three manifolds is a kind of analytic continuation of the notion of a family, of a three-dimensional family of the ordinary three manifolds of the volume form. Now, there is a relative of this BCOV, Kodaira-Spencer Lagrangian, which is I mean, I didn't try. I mean, I described it in words, so you already know what it is. But you could guess from the fact that scaling forms on the real algebra of vector fields was not local, it involved taking D inverse of the vector field. That Lagrangian is very non-local. So about 20 years ago, Hitchin came up with a more sort of local-looking Lagrangian whose critical points give you Calabi-Yau structures. And some time ago, I recast it in a kind of polynomial. So his Lagrangian was not polynomial, but local. So I recast it in slightly more polynomial forms. And it's sort of similar in spirit to this Euler Hamiltonian. So let me just remind you, maybe you'll find it useful in your. So you start with a closed six manifold. Let's say you fix some almost complex structure and using it, you can define the first Chern class, and it's 0. And then, so the Lagrangian, this functional, Hitchin functional will be defined on the space of 3 forms, endomorphisms of the tangent bundle, and 6 forms. So that it has 3 arguments, phi, j, and mu. And it's polynomial in those variables. So now you fix phi to be a closed form, and you extremize this polynomial functional with respect to all 3 objects, phi, j, and mu, except that you keep the cohomology class of phi fixed. So you can shift phi by an exact 3 form, so d of some 2 form, and you can vary j and mu any way you want. So mu is essentially a Lagrange multiplier. It's just normalizes j so that its trace j squared is equal to -6. And then it turns out, so essentially Hitchin's analysis of dimensions of orbits of GS6 in the space of 3 forms tell you that the j, which will extremize this Lagrangian, which is, you see, it's a linear equation for j because the function is quadratic, will turn out to be actually a complex structure. So j squared will square to -1. And the fact that you extremize with respect to phi will imply that the structure is integrable, highly trivial. And then out of phi, evaluate the extremum and phi to which you apply this complex structure j, you can construct a 3 form which happens to be holomorphic physics. And I think, I don't remember what was the argument why it doesn't vanish. I think it was some argument. If this extreme exists, so it might be that it doesn't exist. But if it exists, then you can have a collaboration. Okay, so there's some similarity between the Euler Hamiltonian and Hitchin functional. However, all this is too idealized. We don't want to describe ideal liquid because we want to ideal fluid because we want to. The goal is to understand something about the relativistic fluid dynamics, and because of Lorentz contraction, things get contracted in a way you don't like them to be contracted, so you cannot really have an incompressible fluid once you start moving with velocities close to the speed of light. And so, but Euler, of course, thought about that long before speed of light was even relevant. And but of course there were compressible fluids, and so he wrote equations for compressible fluid. Now those equations involve more variables. So now the density, which I will take to be a 3 form on our 3 manifold, becomes dynamical. And it turns out that one needs to introduce another quantity, which is not really easy to explain what it is. Today we call density per particle. It is slightly, I mean, the notion of local temperature is kind of more intuitive, and entropy is something which is thermodynamically dual to it. But I will not try to make it more intuitive. So there is something called, in order to now describe the compressible fluid, in principle it's actually something very complicated, but there is a class of fluids which are called ideal fluids, for which the energy density, so local energy density of the particles which constitute the fluid, depends this energy density depends only on the entropy and the density. And so this quantity, this energy density, is provided to us by chemists. So they do some measurements in the laboratory, and then that tells you how the fluid responds to changes in volume. Is there a question? No. Yes. Relative? It's a relative. Yes, relative of. Like your brother could be your relative.
But in what sense it is relative of?
Its critical value of Nikita is the real part of the critical value of BCO functions. So they both have something to do with the computing the volume of the collinear manifold with respect to omega wedge omega bar. But they arrive at this critical point by completely different means. In some sense, BCOE, the Cadere Spencer, should be viewed as a classical conformal block for Hitchens theory. Like for Liouville theory, so there is a function of the field phi whose critical points give you the Liouville equation. And then there is this classical conformal block which depends on additional data, but is holomorphic in the complex structure. The Liouville theory, on the other hand, is not holomorphic. It depends on both tau and tau bar. So there is a way of connecting Liouville to conformal blocks and the conjugates, and presumably, so the Hitchens functional also needs some kind of a Carl factorization, which nobody worked out yet, for which would be similar relation. Okay, I'm moving too fast, so please feel free to ask about 3 slides before. So there are some equations. I mean, I don't expect you to memorize them or to understand them. I just want to point out that we have 5 equations of 5 functional degrees of freedom now. So in Euler's case, essentially, so it looked like we had 4 equations because V had 3 components and there was an incompressibility constraint. But now we have so density, entropy, and the velocity, and this energy density is a function of the density and entropy. So the reason why we need to write this energy density is because now the pressure is not completely determined by the distribution of vector fields, unlike the Euler equation, because the liquid can be compressed. There is something internal physics going on, and that's captured by this energy density. Yes. It's a top 4, right?
Pressure is rho squared.
Oh yes, so the first, so it's okay. So the first equation is written in old-fashioned equations. I did not write the first equation geometrically. So to write it, you need to use you need to use the vector. So you need to use what's called musical isomorphism between momentum and velocity. But starting, okay, maybe the last equation is not also so now dot p is just so it's a contraction of V with rho, and then I apply derivative. Okay, sorry, yeah, it's I mean I literally copied it from Wikipedia, but try to geometrize a little bit, but I didn't do the good job. Okay, so now fast forward from Euler to previous century. And so brave gentlemen, Lichnerowicz and then Carter and his collaborators, they try to make those equations look relativistic. So in those equations, time was really separate. There was no relativistic invariance. And so they were trying to recast the equations describing the fluid in a way which will be consistent with special relativity and ideally general relativity, so that you could describe, the neutron stars or collapsing stars, collapsing liquid stars, not gaseous stars. By the way, Lichnerowicz, I think, is the same Lichnerowicz who was famous for formulas in differential geometry, but also one of the authors of the program of information. So there is a connection to quantization through him and through the result. Okay, so here's our proposal with Pavel Wiegmann. So we start with our reformulated. So this is our space-time. And we don't want to separate it to space and time. And I just take it as a smooth formanifold. And now I want to introduce a very simple symplectic manifold, which is associated to it. Namely, you just take the space of all differential forms on M, except for two forms. Two forms will drop out of the formula below, so I just don't take it. So we have a function which I call entropy. We have one form which I call momentum. We have a three form now which I will call flux density, and the fourth form which we call the Lagrangian density. And it is obviously the potential bundle to, let's say, take 2 out of 4. Therefore, it has a symplectic structure, usual symplectic structure. And there are various generalizations which one can do just by looking at this picture. For example, one can deform the symplectic structure by adding this cubic term. So it is, as in Yashna's talk yesterday, this would be an example of the magnetic deformation. So, think of P current PM as a potential to omega 0 plus omega 1. Then this 2 form is pulled back from the 2 form on the space of 1 forms. So it's like a magnetic field deformation of the symplectic form of potential bundle. So this form is important in the studies of the 5-dimensional change dynamics theory. And as such, it makes sense to generalize by making P not a one form, but a connection with some one bundle, maybe on some R bundle. And if it's in one bundle, then this level K can be meaningfully quantized. It is not meaningful to make an integral otherwise. And then there is another generalization where you replace, when you make N with 3 form, also a connection, but now on some kind of a 2-germ. So it's an object which is not locally well defined, but its derivative dn is a globally defined integral 4 form. And so then we have two meaningfully quantized levels. Okay, so the main claim. The main claim is that the equations that hardworking gentlemen Lichnerowicz and Carter wrote for many years can be very simply summarized by saying that they describe an intersection of 2 submanifolds in this interdimensional vector symplectic manifold. One which carries the information about the smooth structure and the symmetry, nothing else, and another which depends on the metric and the chemistry. So, unlike the previous examples where we were studying intersections of Lagrangian submanifolds, this is an interesting kind of novel type, quite kind of novel type of intersection theory where one submanifold is still Lagrangian, the chemical one, and another is coisotropic. But it's coisotropic, but roughly of middle dimension. So it could have been Lagrangian, but it is not. So this entire is coisotropic. Submanifold, I call it brane because I hope that it will indeed become a brane in some sigma model. So this coisotropic brane is just a zero locus of a moment map for the action of some group on my symplectic manifold. And this group is, in the simplest case, just a semi-direct product of the group of diffeomorphisms of my four manifold. I mean, there cannot be anything, just something which comes with smooth structure, and just a Abelian group of smooth functions, just additive group of smooth functions. Now, this diffeomorphisms, I'm just talking about the simplest case when my phase space is just forms, no connections, no fancy stuff. So the diffeomorphisms act on the space nature by Lie derivatives. Now, for this C star action, sorry, C infinity action, there are two interesting choices which happen to be almost equivalent up to diffeomorphisms. So one choice is to do the naive gauge transformations, where we just shift the one form by an exact one form. So this is similar to the Euler non-relativistic Euler case. And another case, which in fact is also similar to the Euler case, because in the Euler case, if you were to introduce the notion of the entropy, it would have been constant along the flow. So in the second case, this transformation is it's a kind of a linear rotation in the space of fields, and it shifts the one form P by the exact one form times the entropy. And there's an accompanying transformation of the fourth form. And so the second choice is kind of linear. It's preferred because it's linear, just like diffeomorphisms act on fields in a linear fashion, and therefore both diffeomorphisms and the second transformation will be generated by quadratic functionals, and automatically they will produce equivariant moment map. In the second case, in the first case, since the action now is just affine, the associated Hamiltonian is linear, and there could be potentially an anomaly, but there is none in this case. And so these are the components of moment map. So I just listed them for you. It's a very simple thing. Notice that the moment map for the action of the group of diffeomorphisms involves one derivative, because the transformation of the fields involve Lie derivatives. So if I want to impose the equation mu equals to 0, it is some kind of a linear first order partial differential equation on fields. And if you think about where these equations take values, you would recognize in the equations mu diff equals to 0 something like the equations for the conservation of the stress energy tensor, which is what hydrodynamical people usually excited about. They say that we don't know the details of the microscopic definition of the dynamics. All we know is that energy and momentum should be conserved. So they try to write those equations and then meditate on them, I would say. So here we just postulate the diffeomorphism symmetry, but we don't say that we perform the Hamiltonian reduction with respect to diffeomorphisms. We only impose the moment map equations, but we don't divide by the action of the group. So this coisotropic brane CG is just defined as a set of zeros of the moment maps. It is coisotropic because the Poisson brackets of mu's with themselves are proportional to mu. So the equations, this is what's called first class constraints. So the equations close themselves among themselves. Now the second equation, the second brane, yes.
Coisotropic levels and Lagrangian by what amount?
So this one is so it is larger by something which is probably as hard as to classify knots. Namely, so if I restrict the symplectic form on this submanifold, it will have a huge kernel. The kernel will be along the orbits of the action of the group of diffeomorphisms. Failure to be Lagrangian is measured by the quotient. The quotient space is has virtual dimension 0. Because so I should have pointed out that you see my phase space, the functional dimensionality of my phase space is 10. S is 1, P is 4, and then so the group of diffeomorphisms has functional dimension 4, and I have also this one-dimensional group. So I'm taking if I were to perform the reduction, I'm reducing the space dimension 10 by 5-dimensional group, so I should get something 0-dimensional. But of course, diffeomorphisms act very complicated. So it's like this problem of classification of knots. So locally everything is trivial, but there might be some global invariants, and so that's the failure of this thing to be Lagrangian. So it's almost Lagrangian, but not quite. I mean, the interesting question for the purposes of embedding this into the problems like information optimization is whether this quotient has a complex structure. Because the good coisotropic branes are the ones which will transfer from homomorphic relation. Yeah. I suspected that it has, but it's anyway. So the second brane is much easier to define, and well, not much easier. It involves a new ingredient, which is the chemistry provided energy density, which is it's a function of two variables, nothing fancy than that. So given this density, you integrate it over the form manifold against the volume form produced by the metric, where you substitute the first argument, this square root of the L2 norm of the 3 form. So this generative function is a function of 2 out of 4 of my variables. It's a function of the entropy function and the 3 form. I mean, that's my choice of the polarization. There are other choices, of course. So you should think of this as the analog of the variety of operas, because it depends explicitly on the metric on my space. If I change the metric, this brane will move. Now, notice that in my description, I completely eliminated vector fields. So I have diffeomorphisms as some kind of symmetry, but vector fields are no longer, part of my description. However, from the data, from this data SP and U, one can derive vector field. In fact, there are several choices. So one choice you can read about in the book by Landau in textbook of hydrodynamics. And that's very non-covariant. I mean, it's of course it's covariant, but it uses a lot of structure. So it's a vector field which you get by essentially it's musical isomorphism. So you take a 3 form and you make it into 1 form using the metric called start. Then you lift the index, it becomes a vector field, and then you normalize it, and you get the vector field. So it's a 4-dimensional vector field whose norm is equal to 1. So that's the vector field which Landau should study. Now there's a simpler vector field which you can define, which is kind of more natural, I would say. It is defined sort of off the cuff. And that's just the ratio of the 3 form and the 4 form. So outside the locus when mu vanishes, this vector field is well defined. And it was discovered by Carter that this vector field has a nice property, which I will mention a little bit later. So it turns out that if you impose the moments for the diffeomorphisms, then the two choices of the abelian symmetry become essentially equivalent. So there's a little identity you can prove, saying that it shows that the moment map for the first type of symmetry, which was Dn, is related to the moment map for the second type of symmetry, which is D of S back then, by a simple scalar factor. And so outside some hypersurface, where this point vanishes, both symmetries agree. So it means that the semi-direct product of these diffeomorphisms with these abelian groups are isomorphic. Probably the global name for the structure would be that as groupoids, the isomorphic. It's too sophisticated for me right now. The beautiful fact about these equations is that now, using this vector field V, again, generically on the form manifold, if you introduce the two-form omega with vorticity dp, well, generically, it will be non-degenerate. If my manifold M is compact, of course, it will have to be degenerate somewhere. But let's say outside this locus where omega squared is 0, it follows from the equation describing the coisotropic brane that the vector field V is actually Hamiltonian with respect to this emergent graphic structure with the Hamiltonian being the entry. And it follows that, as usual with the Hamiltonian equations, you have this Cartan invariant, the circulation of P is actually conserved along the flow. The circulation of the momentum P is transported along the flow along the vector field V. It's not true about for the Landau-Lifshitz velocity U. Therefore, so Landau-Lifshitz they actually have some paragraph in his textbook saying that for relativistic flows, the Kelvin's law saying that the circulation is conserved is violated. They were wrong because we're using the wrong vector. And so this is my claim that the relativistic generalization of Euler's compressible fluid equations found by Lichnerowicz and Carter simply express geometrically the intersections of these two submanifolds. And so there are these, so the relativistic flows are intersections of these two interesting objects. And what I drew, I tried to draw some homomorphic vector, saying that maybe there is some uplift of relativistic hydrodynamics to a kind of lower Fourier theory, studying the intersections in the framework of some infinity categories. And so it suggested that maybe one should think of relativistic hydrodynamics as some kind of a problem in n equals 2 over 2 sigma models, where the Lagrangian and coisotropic submanifolds are in fact the boundary conditions for the sigma model, typical for so some of those were found by Kapustin and Orlov, and maybe the proper perspective to think about this is actually 6-dimensional. So in terms of some theory on the product of the form manifold and let's say a strip. So the strip will represent the wall shape of the sigma model. The boundaries of the strip will be where these boundary conditions are imposed. And this whole 6-dimensional thing might, who knows, maybe it is related to this feature story which I mentioned in the beginning. Okay, so how much time do I have? Oh, -1. Okay, sorry. I have a few remarks. So one is about the stress tensor. So as remember, this Lagrangian submanifold depends on the metric. So if I change the metric, the Lagrangian will change. And the deformation theory of Lagrangian submanifold is well known, and it's locally described by some function on the manifold. And so what species called stress energy tensor is actually the Hamiltonians generating those Lagrangian isotopies. Now I wanted to point out that having this 5-dimensional symmetry, diffeomorphisms plus something 1-dimensional, is sort of reminiscent to the symmetries in general relativity. So if we were to do the Einstein theory, 5-dimensional Einstein theory on the product of time and form manifold, we will be dealing with a group, but it will be realized on a different space, in space of matrix. Let me flash that. So the analogy with gravity suggests that maybe one should not work on a fixed manifold, form manifold M, but allow certain topology changes. And this has to do with the ideas of Onsager on classical quantization. His point was that maybe this circulation integral of momentum should actually be an integer times Planck constant. And so if you think about it, probably this means that my space-time should not be smooth, maybe it should become non-commutative, or maybe it should become a kind of space-time fold. Okay, so there are some further analogies to the geometric Lagrangians, which I'll probably skip. And just to conclude, I hope I can see that this is a very rich and beautiful subject, and I try to recast this problem in a form connecting to several works of Maxim, hoping that maybe you will give us some valuable insight. Once again, so far they're very complicated by saying something very simple. So, happy birthday.
Допустимо, ролл is a mirror.
Oh, yes, yes. Oh, thank you. You noticed. Yes,